All right, so today's lecture is about the ideal gas law. The ideal gas law is basically a law that all gases follow if they were to behave ideally. So let's take a look. What exactly is an ideal gas? Well, unlike a real gas, an ideal gas does not compress into a solid or liquid under low temperatures and high pressures. It does contain particles that have no volume, which is a direct violation of the definition of matter. But the particles contain no volume, and it does not have forces of attraction or repulsion between its particles. So that's what scientists have identified as an ideal gas. So basically, this gas does not truly exist, but we pretend it does anyways in order for this law to work. So what exactly is the ideal gas law? Basically, it's a snapshot of a gas in a particular moment in time. When we looked last week at Boyle's and Charles and Gay-Lussac's and the combined gas law, we learned about what happens to a particular sample of gas if some change is impressed upon it and how that gas will react. In the ideal gas law, it's a snapshot of a gas, so nothing is changing. It's just a mathematical relationship between the volume, the pressure, the temperature, now the number of moles, and some constant value for a particular gas. That's all it is. Here is the equation for the ideal gas law. It's PV equals nRT. And if you recall, P stands for pressure, V stands for volume, N we learned last week, although we did not use it, N stands for the number of moles, R is a gas constant, and T is temperature in Kelvin. Once again, you got to be in Kelvin for any gas law. R is this gas constant. Now, why do we call it a constant? Because it's a number that does not change. So just like a constant in algebra, this number does not change. It's constant. We do have two values for R that we will use in class depending on the unit of pressure. If our unit of pressure is kilopascal, we use an R value of 8.314 liters times kilopascals over moles times Kelvin. If we're looking at atmospheres for pressure, we use the R value of 0.0821 liters times atmospheres over moles times Kelvin. See, all of the units are wrapped up into this constant, and there's a lot of algebra behind this number that we are not going to go into. But the units are all in there so that they cancel out everything in the problem except for the unit that you're looking for. I'll show you in the next slide with an example what I'm talking about. Okay, hopefully you've been writing down some notes, but you have to actually stop the video here and copy down in its entirety this example. Got it? Good. All right, so we have this helium balloon. It's at a pressure of 2.5 atmospheres, and our best bet here is to create a list like I taught you last week. So pressure is 2.5 atmospheres. We've got volume is 4.5 liters. Temperature is 22 degrees Celsius. And remember, we got to add 273. So temperature is 295 Kelvin. And they want to know how many moles of helium. How many moles of helium? So that means we don't know what N is. And then there's a second question, how many grams of helium do we have? And we'll get into that in a little bit. But notice this problem is different than all of the problems that we looked at last week with the simple gas laws for two reasons. One, we only have one set of units. The pressure, the volume, and the temperature are at one particular value. There is no change occurring on this sample of gas. The other thing is that we're talking about moles and grams. If a problem is talking about moles and grams, you automatically default to the ideal gas law. So let's see how we go about solving this problem. We've identified that this problem requires the ideal gas law, once again because the units are not changing, so there's no change in the sample. This is our snapshot that I talked about. Also, we're talking about moles. So we begin with writing the equation PV equals nRT. Now we need moles, so it's better to do the algebra with just the units as opposed to plugging in all of the values and then solving for your unknown. We already know we need n, so what do we do to get n by itself? Exactly, we divide by RT. So let's do that now before we get things real sloppy and messy with all of the numbers and units. When we do this, now we've rearranged this equation algebraically for n. So now n is equal to PV over RT. I'm going to make this a little smaller, so, I'm making the whole thing smaller. Sorry, guys. Okay. By rearranging the variables using our algebraic skills, we now have a plug and chug situation. We literally can plug in all of our units and our numbers and then chug away on the calculator. So let's do that. So we now have n is equal to our P 2.5 atmospheres times our volume 4.5 liters divided by RT. Now we have to decide on an R value. Because we're talking about atmospheres, our best bet then is to use the R value that includes atmospheres. If you did not write down those R values on the last slide, you must get those down in your notes. The atmosphere R value, or the R value that includes atmospheres, is 0.0821 liters times atmospheres over moles times Kelvin. So that's a big old R value. And then we multiply by T, our temperature, of 295 K. Okay, so let's take a look at how everything cancels out. Our atmospheres cancel, our liters cancel, our kelvins cancel, and we're left with moles, which is perfect because we're looking for N. So now we have to plug and chug. When we do this, we get an answer of 0.46 moles of helium. Now, in your calculator, please check this. Make sure you actually get this answer. When you calculate, you're going to take 2.5 times 4.5, hit the division key, open a set of parentheses, then type in 0.0821 times 295, close the set of parentheses, and then hit enter. You should get the 0.46. You need to wrap up, mathematically speaking, the 0.0821 and the 295 because they're in the denominator. If you don't do that, you will go out of order of operations. Okay, the last thing we need to do, now I'm making the whole thing smaller, sorry, is convert to grams. The problem asked us for grams. So, just a recap from our unit with the mole and stoichiometry, getting us some practice and getting us ready for the final in a few weeks. We take our 0.46 moles of helium and we do some dimensional analysis to get rid of moles of helium and go to grams of helium. On the periodic table, the molar mass of helium is 4 to 1 mole. And this gives us an answer of 1.9 grams of helium. Please keep in mind I have kept proper sig figs for both of these calculations. I cannot give us every single example for each variable, but our algebra skills are there. If we look at our ideal gas law, PV equals nRT, let's say that you have to solve for pressure. What do? Exactly, divide by V. What if you need to solve for temperature? Well, let's see. PV equals nRT. If you're looking for temperature, you're going to divide both sides by nR, right? This is where your algebra skills really come into play. So T is equal to PV over nR. We've already done an example with N, so the only other thing we could do is do an example where we want to solve for V. So PV equals nRT. If we need volume, we simply divide both sides by pressure. So V equals nRT divided by the P. Okay? I don't want you to know all of these. I want you to only worry about the ideal gas law as PV equals nRT, and then use your algebra skills to rearrange this equation for whichever variable you're looking for. All right, now it's time for you to go ahead and work on bookwork. Have a wonderful day.